Okay, so today we'll be talking about transmission through barriers, or otherwise known as tunneling. So let's talk about how particles can essentially move um, through walls. And the thing that allows it to do that is quantum mechanics. Because in classical physics, if the energy of the particle is less than the potential in that barrier, then classically, particle rebounds. And that's because it physically cannot get over that barrier. But quantum mechanically, particle will actually go through the barrier and it will decay. And so we'll see this as we talk about tunneling. So to first understand what we're talking about, let's draw a figure. So we're gonna have, let's say, kind of like a number line. Okay? And essentially what we're having is we have a barrier. So let's draw like a box. Okay? So let's say that we have this box here. And this is at some potential called V naught, and the energy is this is on the vertical axis energy. And so let's call this on the x-axis 0, and let's call this the width of the box A. And so you can see that now we've separated this number line into three regions. We have region 1, region 2, and then finally region 3. And so if I were to draw a particle, right, we know that a particle has wave and particle duality. And so what I can draw is I can draw the wave. So let's say it looks something like this. But when it goes through this barrier, this box, it actually is going to start decaying. And when it comes out here, it's going to have a decreased amplitude, diminished. Now, if this was classical physics, this particle wouldn't even be allowed to go through here. But since we know quantum mechanically that the the particle has the ability to tunnel, that's what allows this particle to come out on this end. And so what our goal is to basically figure out what those wave functions are, and then realize what the transmission coefficient is. So we're going to have a new parameter here that we're going to call T, which is the transmission coefficient. And that's going to basically tell us, if I were to blast, right, this barrier with a ton of, let's say, electrons, right, what is the likelihood that I'll see those electrons come out on region 3 versus region 1? So we're going to have transmission coefficient. All right, so let's get started. So first, we have region 1. And so in region 1, we see that basically we can assume that there's no potential here, right? We only have the potential in this box. So it's kind of like a free, you can treat this part as kind of the same thing as a free particle in 1D. And so we have the equation, Schrodinger's equation, which is going to be minus h bar squared, all of that over 2m, del squared, del x squared. This is essentially the Hamiltonian, remember, without the potential. So this is only kinetic energy acting on the wave function. And then we have E psi. Okay. And so if we solve this, you can see something similar to what we saw in the free particle in 1D. If you want, you can reference that video, but essentially what we're going to see is that it has to be e to the plus or minus ikx. And so there I just wrote plus or minus, but here I'm going to write it all out. So we're going to have psi, and I'll denote it psi 1. So we have psi 1. All right. So we have a psi 1 that is equivalent to A, the constant, e to the, let's say this one is the plus ikx, and then we have another one which is different constant minus ikx. This all comes from the free particle in 1D. And so you can think about this positive one as kind of the wave going into the box, and then the minus function, this section, is going to be like the wave that is being reflected, going out away from the box. Because the fact of the matter is not all the particles will be able to transmit through. And so we just want to represent all of that. And so if we solve for k, what we're essentially going to get, these k's are important. We get k1 is equivalent to 2m e over h bar squared. All of that to the 1/2. Okay, so now we have our psi for region 1, and we have our k for region 1. So now we can tackle the next region. So we have region 2 now. So let me scroll a little bit to the side. And so we have region 2. Perfect. And here we don't see the same kind of oscillation. It has to diminish because the energy is less than the potential. And so we don't see that same kind of the same exact function. And so let's write it all out. Once again, that we have h bar squared over 2m del squared del x squared. And this one we're going to call psi 2. Is equivalent to the difference now. We have the difference in the particle's energy and the potential in that box. And you can think about this as the particle doesn't want basically to, the particle can't reach this potential, and so it's being diminished, its energy. And so this is the energy that we want that is coming out here. If I were to draw like a line going across, oh, oh that is horrible. But essentially this line would be dividing these waves in two, and this wave would want to be diminishing down to this line. But yeah, so let's solve for psi. If we were to solve for psi, we would get psi 2 as equivalent to CE, another constant, and we'll call K2. We'll call this K2. I didn't call this one K1. Oh, this is K1. That's K1. So this is CE to the K2x plus DE to the minus K2x. Perfect. And then if we solve for K2, we get K2 equivalent to 2m over h bar squared. And if you want, you can go through and check this, but to save time, I'm just trying to give you what the actual value for k is. And so that is all raised to the 1/2. Perfect. And so now we have region 2. Last region, we'll come over here. We'll say region 3. Region 3. So region 3 is a little bit different from region 1, even though you can still kind of think about it as a free particle in 1D, and we have that oscillatory part now. So we have the imaginary. The one difference is that we don't have this negative value, because remember, this negative value, this was about being reflected, and here we don't really have a barrier. We can't really reflect. We would have no reason for a wave to be traveling, from this back to A, because it's not really rebounding off any wall. So we only have the forward going one, and so um, the psi for this one would be, if let's first write out the Schrodinger's equation for this. So we have this, the kinetic energy operator. Oh, actually, should keep the convention. And then psi 3 is equivalent to, we'll call it A prime. It's a different constant than the one that we saw in region 1, but it's still kind of similar. And then we have another K1 X. And it's important to note that, you know, this K is the same as this K, because they're both basically free particles in 1D. And so this K is the same thing here. The only K that's different is the region 2 one, because region 2 isn't oscillating, it's decaying. And so we don't see that I in either of these because it's not an oscillatory wave function. All right, perfect. So now we have the wave functions for all three regions. So what do we do now? Okay, so what we're going to do now is we're going to introduce that transmission coefficient that I talked about. So we have T, and I'll give you first the formula and then I'll explain it. So we have psi 3 star, so it's conjugate, complex conjugate, times psi 3 divided by psi 1 star psi 1. Okay, so you might be wondering, okay, where did this formula come from, right? Well, if you think back to what psi squared was, right? Psi squared was actually psi star times psi. So the complex conjugate times the other complex wave function. And so the whole point of multiplying these two was in order to get psi squared, which is essentially the probability distribution. So this tells us, you know, in a certain position, right? Um, in a certain position, right? So let's say this is what psi squared looks like. Let's say at this position, we can guarantee basically that there's a good probability that at x equals a, that a particle will be found there. That's the whole point of psi squared. It tells you how probable it is that we'll find the particle in that location or position. And so if we apply that same reasoning to here, we'll see that, okay, this is telling us the probability distribution in region 3, right? So it tells us, okay, where is the particle most likely to be found in region 3? And the same thing is being said for the first, for this one. So it's telling us, okay, where is the particle most likely to be in region 1? And if we divide the two, we can basically tell, okay, well, what amount of the particles that we all had in region 1, because that's where all the particles were at some point, how much of them are basically in region 3? And so if we divide the two, we get kind of a fraction or like a percentage of how many of those particles we're able to get from region 1 to region 3. And that's the whole point of this. We're dividing the two probability distributions so that we can figure out how many particles are basically getting through, and that will tell us the transmission coefficient. And so if we simplify this, we have already what psi 3 equals. We know that psi 3, here, so we know psi 3 is this, and we know psi 1 is this. And so basically the e to the I k1x, those are going to be canceled out, and it'll all simplify. This will simplify down to the constants. So we get a1 star, here, a1 star, or a prime star, not a1, times a prime divided by a star a. So this is what this comes down to, essentially. Okay, so now we have what the transmission coefficient is. Where do we go from here? Perfect. So here's a good time to introduce one of quantum mechanics postulates. So we have a postulate that basically says the whole point that allows these particles to go tunnel across the barrier is that the wave function, psi, its first derivative, so del psi del x in this case because we're doing 1D, as well as the second partial derivative, so del squared psi over del x squared. These are all continuous and psi has to be finite. So it has to have values and it has to be continuous. And so we can't basically, if we were to go up, we can't see any abruptness. Basically, these values at these boundaries have to be equal. So whatever the wave function at psi 2, its value at, at x equals 0, let's say, and the value of psi 1 at x equals 0, they both have to be the same in order for it to be continuous. And so we can utilize this to get some equations that we can use to then solve for the unknowns, which are the constants. So let's go ahead and apply those. So we have x equals 0, and what we can say now is that psi 1 is equivalent to, actually, let me, psi 1 of 0 is equivalent to psi 2 of 0. So what does that mean? That means that a plus b equals c plus d. Okay, perfect. Now we also have the first derivative, and so we can also say, let's actually number our equations that we got. So then we have another one, which is del psi 1 and del x at x equals 0 is equivalent to del psi 2 del x at x equals 0. And so what that simplifies down to is I k1 of a minus b is equivalent to k2 c minus d. So that's our second equation. Okay, perfect. So now we have the two equations from x equals 0, but what about the other boundary? We need to do that one too. And so I'll draw a line here, but we have essentially x equals a. And so we have psi 2 at a is equivalent to psi 3 at a. And so that simplifies down to ce to the k2a plus d e to the minus k2a is equivalent to a prime e to the I k1 a. Right, perfect. Okay, and then we have also the derivative, which is, so let me, the third equation, and then we have del psi 2 del x at x equals a is equivalent to del psi 3 at x equals a. Perfect. And so substitute in, get a very similar equation. Okay, and that is going to be our fourth equation. Okay, so now we have four equations. What are we solving for? We have four equations, but we have five unknowns. So what are those five unknowns? We have a, b, c, d, and a prime. So where can we get this fifth equation from? Well, we also have the transmission coefficient, which basically says that we have this. Okay. And so now we have our five equations, five unknowns. You can go ahead and punch this through a solver, but I'll just give you what this gives. And so if we solve for the transmission coefficient, we essentially get 1 plus e to the k2a minus e to the minus k2a, all of that over 16 epsilon. So I'll tell you what an epsilon is. All of this to the minus 1, where epsilon is essentially the ratio of the particle's energy to the potential of the barrier. And so this always has to be less than 1, remember, for tunneling. Because if, I guess I didn't address this earlier, if the energy of the particle is actually greater than the potential, there would be no need for tunneling. It would just go over, right? If we have enough energy, there's no need to worry about going through here. It would be above. So it would be like going over here. It would go fly right over the barrier. So we need to have, for tunneling, the energy to be less than V naught, because otherwise there's no reason to tunnel through the barrier. But yeah, so that's what epsilon is. And you can also rewrite this transmission coefficient if some of you math people might recognize that this is like you can rewrite this as sinh, the hyperbolic sine function. And so you can rewrite this as a sinh function, and then the bottom would become a 4 epsilon, 1 minus epsilon value. But yeah, so this is essentially how to find the transmission coefficient for particles for tunneling through. I'll catch you in the next one.